Hello, welcome. In this video, we're going to be working Algebra 2 Unit 6 review. Okay, so we're practicing for our test over polynomials. Okay, graphs of polynomials. And so we're going to write a polynomial function in standard form based on the graph. Okay, and so what we do usually with these is we start with the x-intercepts and then we need one other point to determine the leading coefficient. Okay, so I've got intercepts at x equals, that's negative 1, 2, 3, 4. X equals negative 4. X equals 0 and x equals 1. Okay. And all of these are single roots, I know, because the graph is passing through the x-intercept confidently. Okay, so they're all single roots, so I'm not going to have to say like x minus negative 4 squared or to the third power or anything like that. So I'm going to have x minus negative 4, whoops, x plus 4, times x minus 0 times x minus 1. Okay. And it's going to be y equals some number times that. And I'm going to have to find some other point that goes through. I'm going to use this one. I mean, I'm not certain that went through that point exactly, but I don't really see anything else that's looking more inspiring than that one. I don't see any other grid spots. Okay, I think I'm going to go with it. Okay. And so I'm going to just probably figure out A right now. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so when x equals negative 2, y equals 12. So I'm going to have 12 equaling A times negative 2 plus 4 times x, which is negative 2, times x minus 1 would be negative 3. Okay, so negative 4 times negative 3 is positive 12. A equals 1. All right, so now I'm going over here and I'm saying y equals x plus 4 times x minus 1 times x. I think I'm going to multiply these two together, get that out of the way, and then distribute it in the x, because that sounds kind of easy. Okay, with a equaling 1. So if I multiply these together, I'm basically unfactoring, and I'm going to have x squared. I would add these two numbers. That's positive 3x. I would multiply these. That would be negative 4. I'm still multiplying that by x, and so my standard form equation will be x to the 3, 3x to the 2, and negative 4x to the 1. Now we're going to sketch a graph of the polynomial using the multiplicity of roots and in behavior. Label the x-intercept, label the y-intercept. Okay, great. So I'm seeing 3 powers of x from this triple root here, but then I'm seeing 2 other factors that each have 1 power of x. So in total, this is going to be a degree 5 polynomial. The leading coefficient is going to be negative because of this negative out here. Okay, so if I've got an odd degree with a negative leading coefficient, I know that the end behavior will look like this. The end behavior will be, okay, odd degree, negative leading coefficient, looks like negative x cubed. Okay, so it'll, at least on the edges, on the far left and the far right, it'll look like this. All right, and now I'm going to draw myself an x-axis. I'm going to label it with the zeros. X equals negative 2, x equals positive 1, x equals positive 4. And I'm going to start with the end behavior. It's coming from above and going down as I move left to right. So I'm going to start up here. X equals negative 2 is a single root, so this graph is going to pass through here confidently. X equals negative 1, also a single root, going to be confident there. But x equals 4 is a triple root, so it needs to hesitate before it passes through. So it's going to come back down. And hesitate as it goes down through. Okay. And that's going to be a sketch of the polynomial. Now, we would need to also put in a y-axis here, because it said label the x-intercepts and the y-intercepts. I'm going to just put in, like, we don't know where that y-axis sits with respect to that relative maximum over there, but calculus to determine that. Just give it the best guess we can. Okay, and for us, we can figure out the coordinate of the y-intercept, right? We know it's going to be positive, but that's going to be f of 0 equaling negative 0 plus 2 times 0 minus 4 to the third power times 0 minus 1. All right, so I've got, let's wait a second. Did I do something wrong here? Yes, I definitely did. I said that the root was at -1 when it is clearly at +1, so that's going to become a +1, that x-intercept, which means that this is no longer the location of the y-axis. Okay, so I'm just going to have to, I'm not going to re-record the first problem or anything. I'm just going to ask for your forgiveness and just remind you that we all make horrible errors sometimes. I'm just trying to get rid of this y-axis. Okay, yeah, looks great. So there we are, and that's x equals +1. We're calling that in, and so I'm going to say that the y-axis is there, and now the y-intercept will be negative. Okay, that makes more sense. Okay, 4 to the 2 is 64. No, 4 to the 3 is 64. 64 times 2 is 128. Triple negative makes negative, so that's -128. Okay, that was something. Okay, but now we have a good sketch that with labeled x-intercepts, y-intercepts. It's correct. It's not wrong. That's all we can really hope for. All right, now we're going to write a polynomial in standard form with rational coefficients that has the given zeros. Okay, so that rational coefficients bit does matter. For those of y'all that are trying to catch me on the fine print. So x equals -1, multiplicity 2. Okay, so that's going to be, and it just says a polynomial, so I don't need to worry about the leading coefficient. I could make it something else if I wanted to. I'm just going to assume the leading coefficient's 1, though. So x minus -1, multiplicity 2, x minus 1. Okay, got this. This is, I've seen worse, I guess. Okay, if I square x plus 1, I'm going to multiply x plus 1 times x plus 1, and I'm going to have to do FOIL. Okay, and what I'm going to get is x squared plus 2x plus 1. Okay, don't forget that 2x. That's the common mistake. Multiplied by x minus 1. And I think, well, I'm going to do this the old way because I don't really have enough room on my sheet to do the box technique with how big I'm writing. So what I'm going to do is I'm going to multiply x by all three of these. And then I'm going to multiply -1 by all of these and kind of like, align them. So -1 times x squared is -x squared, -2x, and -1. I think this is how they told me to multiply, things larger than binomial by binomial. It's like line it all up that way. And then add down. So I got x to the 3 plus x to the 2 minus x minus 1. Okay. I think I might have been smarter to say that I could have combined one of these with that, and I could have had x plus 1 times x squared minus 1. Yeah, that would have been a little smarter, but whatever. All good. Okay. Now in B, if we know that if we're going for rational coefficients and we know that x equals square root of 3 is a root of this polynomial, then we know that x equals negative square root of 3 is going to also need to be a root of the polynomial. So what I'm going to do is I'm going to say, all right, I'm starting with x minus -1, and then x minus square root 3, and x minus the negative square root of 3. And I'm going to choose to multiply the second and third terms together. They look like they go together, right? It's something that's going to give me a difference of 2 squares when I multiply it out. So I'm going to say this is x plus 1 multiplied by x squared minus 3, okay, because the square root of 3 times square root of 3 is 3. Okay, and then I'm going to multiply this together, and I'll have x to the third plus 1x squared, negative 3x, and -3. Okay, and that's going to be a standard form polynomial that has rational coefficients and these zeros. It's just that you can't get a rational coefficient standard form polynomial that has only these 2 zeros. You have to have the third one to make sure the coefficients are rational. Okay. Solve the equation, give the multiplicity of each solution. Okay, so probably we're thinking factoring, right? Okay, because we're not going to use the cubic formula on this or the quartic formula. We're going to solve by factoring. And if that doesn't work, then we'll try using rational root theorem stuff. So over here, I'm going to start by, I wish that I could factor out that 3. I mean, that 2, but that 3 is standing my way. The good news is that the ratio of 2 to negative 3 is going to be the same as negative 8 to positive 12, so I'm going to be able to use group and factor. I factor out 2x squared from the first 2, and I'm left with x. Well, not going to be factoring out 2x squared. I'm going to be factoring out 1x squared because it's the same issue that I ran into before. Let's switch up the color. All right, so x squared multiplied by 2x minus 3. That was even worse than when I tried to use the felt pen. Okay. What's the greatest common factor here? That would be minus 4. Okay. Times 2x minus 3. Okay, yeah, that's looking good. So I'm going to factor out the 2x minus 3. I'd be left with x squared minus 4. And if I'm just going for the solutions, then I'm going to get it to the point where I can solve, get the factors down to where I can solve. Like, you could factor this more, but I'm just going to say, okay, 2x minus 3 equals 0. I can solve that. Okay. Or x squared minus 4 equals 0. I can solve that also directly. Okay. So x would be plus or minus the square root of 4, so that would be x equals 2, x equals negative 2. I am just going to say, okay, multiplicity, these are all single roots. No, that would be enough. All right, and B, we've got a 4th degree polynomial, and this one's going to be factorable using that substitution technique, right? We've got 4th power, 2nd power, no x's. Okay, so this is going to be like x squared plus some number and x squared plus some other number, where those numbers multiply to positive 81 and add to negative 18. So I'm going to say, just in case it had been a while since you'd done one of these, let u equal x squared so that u squared equals x to the 4. Then I'm working with u squared minus 18u plus 81. Okay. Then I'm going to go over here and I'm going to factor, okay, hey, this is u minus 9 times u minus 9. Not u minus 9 to the 9th. Okay, and that needs to equal 0. Okay. But u is x squared. So I've got x squared minus 9 squared equaling 0. And x squared minus 9, that can be written as x plus 3 times x minus 3. And if we're squaring that whole thing, then we're going to have 2 copies of x plus 3 and 2 copies of x minus 3. Okay, and that will give me x equals 3 and x equals negative 3. And these are both double roots because they both have that exponent of 2 on them. Right. Now, I'm going to give the degree and leading coefficient of this one. Okay, degree is 4, leading coefficient is 3. Okay, look for the highest power of x and you've got it. Degree 4, leading coefficient 3. Okay. Then we're going to find the zeros and sketch the graph based on our understanding of multiplicity and end behavior. Okay, well, if I've got an even degree polynomial with a positive leading coefficient, then the end behavior will look like kind of like y equals x squared. Right? It'll go up on both sides. Okay, so I need to factor this, so I'm going to factor out a 3 first. Okay, I'm going to factor this with x squared because I see this is what's happening. This is very much like the other one. I'm going to say this is going to be x squared minus 1 squared. And because I just did this one that worked the same way, I know I'm just going to get x plus 1 squared, x minus 1 squared. Because this breaks up into x plus 1, x minus 1. Okay, so I go over here, I draw in an x-axis, I plot my x-intercept, and then I'm going to, okay, observe the end behavior, and then just kind of like respect the fact that, okay, x equals negative 1 is going to be a double root And so is x equals positive 1. Okay, so these are both going to be bouncing. And there we go, we've got a sketch. All right, now we're going to use this graph to answer some questions. All right. All right, so I kind of lost my place. I had a meeting and came back. So, what intervals is f increasing? Okay, well, that's going to be where it's got a positive slope, or where is, as I move left to right, the graph is going up. So from A to B and D to E. Okay, on what intervals is f decreasing? Okay, from B to D. Okay, where does it have a local maximum? That's x equals b, and where it has a local minimum, that's going to be x equals d. All right, let's move on. All right, the graph of f of x is shown below. What's the y-intercept on the graph of f? Well, that's going to be f of 0 equals, if I plug in 0, I'll get 0, 0, 0, 0, 0, all negative 4. Okay, great. What's the degree of f? It's the highest exponent of x that I see. That's going to be degree 4. Find the roots of f and give their multiplicities. Okay, well, it's looking to me like I got a double root over here at x equals negative 2, so I'm going to try to do synthetic division, hopefully twice, and maybe that'll knock out a couple of degrees, and I'll have a quadratic that I will be able to either factor or use the formula on. So 1x to the 4, 3x to the 2. No, where was the x to the 3? I need to put in a 0 to account for that, right? Y'all know that. It seems like y'all are probably actually a little more reliable on that than I am. I just kind of get a little carried away sometimes. So 1x to the 4, no x to the 3, 3x to the 2. Oh. It's like I'm trying to delve into my own error here. I bet I typed this wrong and that this is supposed to be 3x to the 3. I was like, this looks really long to be a 4-3 polynomial with a missing term. Okay, so I'm just going to go and erase this once again and just write over it again. I'm going to work this one as if it's 3x to the 3rd, and then if negative 2 is not, if negative 2 is not a root of that, then I don't know what I'm going to do, but cross that bridge and come to it. I'm going to say 3x to the 3rd. I'm just going to assume that's a 3x to the 3rd. Negative 1x to the 2, negative 8x, and negative 4. And then we're going to be plugging in x equals negative 2 and divide by x plus 2. And so I get 1, negative 2, 1, negative 2, negative 3, positive 6, negative 2, positive 4, 0. There we go. That's a good sign. Okay, so yeah, I think that was the error. It was a typing error. Okay. Next, I'm going to try negative 2 again because it looks like it's a double root, so it should be able to go through twice. 1, negative 2, negative 1, positive 2, negative 1, positive 2, 0. All right. So what that means is that since I've divided by x plus 2 twice, I could say f of x, if I factored out x plus 2 twice. That's basically what I did when I did that division. And I'm left with an x squared minus 1x minus 1. Okay. And so find the roots of f and give their multiplicities. X equals negative 2 is a double root. Okay, this is not something I know how to factor, so I'm going to have to use the quadratic formula. So x, okay, that thing could equal 0. The thing in parentheses here is trinomial. When x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so 1 plus or minus the square root of 5 divided by 2. Those are both single roots, each of those. So x equals 1/2 plus root 5 over 2. That's a single root. Okay, x equals 1/2 minus root 5 over 2 is also going to be a single root. And those are the roots and their multiplicities. Okay, so let's move on. All right, figure graph of a third-degree polynomial. Write an equation for p in factored form. Okay, I've got a root at x equals 0, so that means x is going to be a factor. And I've got a double root here at x equals 3, so I'm going to have x minus 3 as a factor twice. Okay, and that's going to be factored form. Now, there could be a leading coefficient, but there's not really enough information for me to determine what that is, right? If I had, okay, well, I know what the y-intercept is because x is a 0, because x equals 0 is a 0. But say, I had the coordinates of that point right here. If I had the y-coordinate of that point, I could determine the leading coefficient. I just need one more point. And then we're going to write an equation for p in standard form, an equation that could represent p. And I'm going to start by squaring x minus 3. Okay, so do that off to the side in blue. Right, so x minus 3 times x minus 3, when I multiply that out, I get x squared minus 3x minus another 3x plus 9. That's x squared minus 6x plus 9. So what I've got is x multiplied by this x squared minus 6x plus 9. Okay, and then I'm going to distribute this x across all three of these terms, and I'll say, all right, x times x squared, that's x to the 3, x times negative 6x is negative 6x to the 2, and x times 9 is positive 9x. Great, happy, move on. All right, now we're going to match the equation to the description. Okay, I put this on there for a reason. Realize that, I always talk about the degree of polynomial, and I use this like degree 3, degree 4, degree 5, degree whatever. But there's other language that other people will use, like cubic, quadratic, quartic, quintic, polynomial, all this stuff. So I didn't want you to forget about that. So quadratic, that's a degree 2. That's a degree 2 polynomial. And so that's going to be a of x. And that's a degree 2 polynomial. Right. A cubic polynomial is a degree 3. Okay. So the degree 3 polynomial is the one where I see x cubed. That's going to be right here. And the fact that I have square root 5 times x cubed, that's okay. It's still a polynomial. It just doesn't have rational coefficients. But, we said cubic polynomial with rational coefficients is cubic polynomial. So that's going to be c of x. Right. Quartic polynomial, that's degree 4. Okay. This is going to be degree 4 because although, like this is going to not be a polynomial because of the dividing by x or the negative powers of x, taking x to the 4 and dividing by 3, that's like 1/4 or 1/3 of x to the 4th. And that's just a number. Okay, so quartic polynomial is going to be b of x. I think oftentimes in an algebra class what they tell you is that you can't have like fractions with x's in them or radicals with x's in them. So I'm going to try to trick you by like putting or pointing out where they're kind of wrong about that, where something with a radical doesn't necessarily mean that you don't have a polynomial. Something with it, just because you've got a fraction doesn't mean you don't have a polynomial. Okay? This is not a polynomial because it's a negative power of x. Polynomial is like we've got to have just positive whole number powers of x. Okay, so not a polynomial is d, and I suppose e, you could paint with the same brush, but I need to save e for not a function. Now, whether something is or is not a function, not really something we've talked about in this class. You didn't talk about it in Algebra 1, I know, because it's on the end of course exam for our state, but what would make something not a function, to your understanding or in your experience, is not passing the vertical line test. And, I'll just plot one instance of this function, this equation not being a function. Maybe I'll say this is x equals 9. Okay, if e of x is equal to plus or minus the square root of x, okay, it's going to be plus or, so y is 3, or maybe y is negative 3, and that's not passing a vertical line test. Okay, so it's not a function. Okay, but that's not really something for this test. That's just something to remind you of. And I needed you to be reminded of the cubic, quartic, language. That's important. Okay, so a and b are two positive integers with a being the lesser of the two. Sketch the graph of y equals negative x times x minus a cubed times x minus b to the 2 in the space below. Okay, now this is a little beyond what I would probably ask you on a test because of the degree. The problem is when you have a triple root, it just really pushes the degree up really high. But that's a different discussion. I'm seeing 3, 4, 5, 6 total powers of x in this polynomial. Okay. So I've got a degree 6 polynomial. It's going to have a negative leading coefficient because of that negative out there. So I'm going to conclude that its end behavior is not going to go behind. Nope, not going to go behind my face. So it's going to look like y equals negative x squared. Okay, these are the two sides. So move this horizontal line up a little bit, I feel like. Anyway, I'm going to say, all right, it comes from below. X equals 0 is a single root because this has got an exponent of 1. This one's going to be a triple root and then a double root. So, single root, triple root, this is going to be pretty ugly. Double root, oh man, yeah. This is definitely not the best polynomial sketch I've ever drawn, but this would be good enough to get full credit if this was a test question. It's got the right end behavior. It's got the right behavior at the zeros. It fits together. There's no extra zeros. Okay, one thing I'll say is that with these sketch the graph problems, why I always start with labeling the x-intercepts is that if you have any other times you cross the x-axis besides those x-intercepts, you've drawn it wrong, right? Because you've found the x-intercepts first, presumably. So it's like if I was crossing back over here to make sure I hit the end behavior, I need to stop and reassess because I made an error somewhere. Now we're going to find the zeros of these things and give their multiplicities. Okay, I was like, I didn't leave myself nearly enough room to work this, but I'm seeing that these are relatively simple equations, and I remember making this, and I really liked this. I think that this would be a good example. Okay, so we're going to start by factoring on all of these, and we'll say what's a common factor. Okay, so I can factor a 2 out of both of those. I can also factor out an x to the 3. And then I'll be left with, okay, I would multiply 2x to the 3 by x to get 2x to the 4, and minus 25. Okay, so that means that x equals 0 is a triple root. And then I'm going to take, wait, what am I doing here? Oh yeah, x equals 25. That's going to be a single root. This 2 here, that's not going to contribute any roots because 2 is never equal to 0. The only way that 2 times x cubed would be equal to 0 is if x was 0. So that's why that's contributing that 0. Okay, but anyway. Now I'm going to do the same thing. I'm going to factor out 2, but only 2 powers of x this time. So it's 2x squared times x squared minus 25. And I can factor this a little bit more. So that's 2x squared times x plus 5 times x minus 5. So now I'll have 3 roots this time. I'll have x equals 0, which is going to be a double root because of the exponent of 2. Okay, I'm going to have 5 and negative 5, and those will both be single roots. Did it once. And now, okay, I've got 2 more, but I'm just going to kind of keep factoring the same way, always starting off factoring at least 2 and maybe something else. This is going to be 2. 2 is all I can factor. So x to the 4 minus 25. Okay. And then when I factor this a little bit more with a difference of 2 squares, I'll have x squared plus 5 times x squared minus 5. Okay. Now, x squared plus 5, that can never equal 0. Okay. Just think about it. Take a real number, square it, it's going to be positive. Add 5, it's going to be more positive. It can't be 0. Okay. X squared minus 5 could potentially be equal to 0. Okay? And that's going to be the only thing that's giving us any roots, because 2 can never equal 0, so it's not going to produce any zeros of this polynomial. So I'm going to say x squared minus 5 equals 0. X squared equals 5. X is going to be the square root of 5. I guess I just finished my thought over here. X is plus or minus the square root of 5. So x equals square root of 5. X equals negative square root of 5. Both of these are double roots. Oh, no, pardon me, single roots. Well, I would have thought that. But what was I going to say about this? Oh, so it's like up to this point, we've seen a lot of times 4-degree polynomial, we expect to have 4 roots up to including multiplicity. But I'm only seeing 2 single roots here, and it's a 4th-degree polynomial. And it turns out that there's like a couple of hidden ones, and we'll be studying that in the next unit. Now the last one in this set is going to be, all right, I'm going to factor out a 2 and an x. I like where this, I remember thinking about this. I like where this one's headed. So, okay, I can either have 2x equaling 0, and that would give me x equals 0. That's going to be a single root. Or I could have x to the 3 minus 25 equaling 0. And I can solve that directly because I don't have any other x's, so I'm just going to say x to the 3rd equals 25, and x equals the cube root of 25. You do not need a plus or minus when taking the cube root of both sides of an equation because the cube root of a number is unique. A given number, you give me a number, there's only one cube root of it. So that's also a single root. Okay, so I'm just going to kind of say both of these are single root. Okay. And, you know, cube root of 25, I can't think of a number. It's like a little bit less than 3, right? It's probably pretty close to 3. I'll let you try to figure out what that is. Right. Write a polynomial with rational coefficients and a minimal degree in standard form with a triple root at x equals 0 and a single root at x equals 3 minus the square root of 5. These problems, they're good algebra. Honestly, like they're not exactly like this, but I remember doing some problems not that far off from these with these minimal polynomial problems when studying like modern algebra in, you know, at the end of my time studying mathematics at the university. So this minimal polynomial problem, it could potentially come back in the future for you if you just keep taking these algebra classes, you know, algebra 9 or whatever it was, you know, might work the same kind of. So triple root at x equals 0, single root at x equals 3 minus the square root of 5. I'm thinking, okay, x to the 3, single root at x equals 3 minus the root 5. So I'm going to say x minus 3 minus root 5. And then multiplied by, well, if I'm trying to get rational coefficients and x equals 3 minus the square root of 5 is a root, then x equals 3 plus the square root of 5 needs to also be a root. Okay, so x minus 3 plus square root of 5. Okay. I'm going to multiply these all together. And I'm going to use the box. So x, well, I guess, okay, I'm going to need to distribute these negatives. But I feel like I've done this enough. You've seen me do this enough that I might not just write a new line with it. This is going to be x minus 3 plus the square root of 5, because it's minus the negative square root of 5. Okay, and I'm multiplying this by x minus 3 minus the square root of 5. All right, and now I'm just going to fill out the box. Minus 5. Okay, so notice, just like always, these terms that have any sort of irrational number in them, they just cancel off. Okay, it's really nice. So what we're going to do is say x squared minus 6x plus 4. needs that x cubed distributed across. Okay, so this is x to the 5 minus 6x to the 4 plus 4x to the 3. That's it. All right, now on this one, we're going to do some sketching and determining increase, decrease. Okay, so this is going to be a third, fourth degree polynomial with a positive leading coefficient. Okay, I'm counting the number of x's. I see 1x and then 3 powers of x is total d4. Positive leading coefficient means my end behavior is going to look like this. Okay, it's going to have zeros at x equals 1 and x equals 4, which is a triple root. I think I'm only going to be writing the multiplicity if it's not a single root for the problems on this page. And then I'm going to, kind of sketch my graph. So x equals 1 and x equals 4. So it's coming from above based on the end behavior. And then it's passing through confidently here, hesitating there. Okay, x equals 0 is to the left of this. So it's, happening right there. And if we thought about what's happening to the graph in that moment, as I move left to right, the graph is going down. I'm going to say it's decreasing. And this next one, we're going to have to factor this one on our own. That's okay. We haven't done a whole lot of factoring in this video, so it's good that we practice our factoring. That's one skill I really need you to have when you're done with this class. So I'm going to group and factor out an x squared, factor out a negative 16. A lot of group and factor in this class. But that's good, that's healthy. I don't know how much group and factor we're going to be doing in pre-cal, and I know how much we're going to be doing in calculus. Not a whole lot, but it's a good skill to have. So I'm going to factor out that x minus 2. I'll be left with x squared minus 16. Keep factoring. All right, pardon me, I lost my place. I forgot what I was saying before I paused. But, x minus 2, x minus 4, x plus 4. Okay, we got our factors. This is a degree 3 polynomial with a positive leading coefficient, which we could tell really easily when looking at standard forms. It's like, standard form has certain advantages and certain disadvantages. I'm going to plot my zeros, negative 4, positive 2, and positive 4. And it's third degree, all single roots, so it's just going to, third degree positive leading coefficient, all single roots, so it's going to come from below. Okay, just like that. Oh wait, no, not just like that. I have to determine if the function's increasing or decreasing. X equals negative 4, that's going to be increasing. Okay, because if I look, just right here, as I move left to right, the graph is going up. Okay. Does x squared times x minus 10 cubed have a local maximum, a local minimum, or neither at x equals 10? Well, I'll tell you right now, I can already tell that this is going to be neither. Because that's a triple root. And we know at a triple root, the graph does hesitate, but it does change signs. So it looks like, it's coming up, and then it decides to go, well, it's increasing. Or, the opposite could happen. It could come down, hesitate, and then go down. In that case, you would still be decreasing, and you're not having a maximum or minimum. I'm going to draw the diagram anyway. It's a fifth degree polynomial with a positive leading coefficient. Okay, so that means that the end behavior is going to look like y equals x cubed. Okay, odd degree, positive leading coefficient. And then my zeros are going to be x equals 0 from that. That's going to be a double root. And x equals 10 is going to be a triple root. Okay, so it's coming from below. It's going to bounce at x equals 0 because of the double root. And then it's going to hesitate but pass through at x equals 10. All right, and there you have it. at x equals 10, that is neither a maximum nor a minimum because the graph is not changing from increasing to decreasing. Okay? Or the function h is not changing from increasing to decreasing. It's going from increasing to hesitated to increasing again. Okay? There you go. All right. Now, got another max min neither question. Okay, this one is probably going to be one or the other because it's double root. Double roots, those end up being maximum or minimum. Anyway, so this is going to be a second third-degree polynomial with a negative leading coefficient, which means that its end behavior is going to be it comes from above and then it goes down. Okay? And I forgot what I was thinking here. Oh, it's already factored, so I just list out the zeros. X equals positive 1, that's a single root. X equals negative 2 is a double root. And it's a double root because of that exponent right there. Right, and then I'm going to go over here. X equals negative 2. X equals positive 1. Degree 3 with a negative leading coefficient. Okay, so I just need to be careful with the double root, okay, which is this one, so it's going to bounce. And it's going to go right on down through there confidently because that was a single root. We don't really even care that much. We're interested in what's happening right here, and it's hitting a local minimum. Okay, so I say relative minimum. Okay. Find the value of x at which g of x equals x squared minus x plus 6 has an extremum. Is it a maximum or a minimum? I know I've used this word out loud in class, but I know that I've written it on any of the documents you've seen. An extremum is a maximum or a minimum. Okay? And okay, this is a second-degree polynomial, which means its graph is a parabola. It's got a negative leading coefficient, so we know what this graph is going to look like, right? We know that it's looking like that. Okay? And so it's a maximum. And in that quadratic unit, now, I mean, we could factor this thing, find the zeros, and say, hey, the maximum is going to be halfway in between the zeros. That is true for a parabola. But we learned a formula in Unit 4 where, the x-coordinate of the vertex. So that's what I'm going to use. So it's going to be a maximum at x equals negative b is 1 over 2a is 2 times negative 1. And so that's x equals negative 1/2. And that's a maximum because it's a downward facing parabola. Okay, so I just thought I'd remind you of that, of something that we already had learned about in this class, our new knowledge in a different way. Oh, I was hopeful. I flipped the page and I saw a blank sheet and I thought maybe I was done. But we're not even close to done. I think there's over 20 problems on this review. This one's pretty robust. This one might be best done in multiple sittings. But that would be the best way to study for the test, right? Just keep practicing it over the course of a few sittings. Okay, find all solutions. This is where I think we would need to use the rational root theorem potentially. I'm going to think to myself, does 3 divide all of these? It does not divide 37. Okay, so now we're thinking of factors of 12 divided by factors of 3. I'm going to start with 1. Okay, so let's just test real quick. Add the coefficients, see if they add to 0. 3 minus 2 is 1. 1 minus 37 is negative 36. Plus 36 is 0. X equals 1 will be a factor of this thing. I'm just hoping for the best past that. Okay, so 3x to the 4, negative 2x to the 3, negative 37x squared, positive 24x, and positive 12 with x equals 1, because I just checked and saw that was going to work. Drop it down, multiply, add, multiply, add, multiply, add, multiply, add. Get 0. Great. Happy. And look at this. This is group infactorable, right? 3 to 1 is the same ratio as negative 36 to negative 12. So I'll be able to work with this. So we're going to go over here, and I have this x minus 1 that I divided out, and then I'll have 3x to the 3 positive x squared negative 36x minus 12. Okay, and this is still equaling 0 because I'm trying to solve this equation. Okay, then I'm going to do group and factor. And I'm factoring out a negative 12 times 3x plus 1. Okay, so I've got x minus 1 times 3x plus 1 times x squared minus 12. And I think this is far enough that I'll be able to solve each of these factors out individually, and I'll be able to get all of my solutions. Okay, this is going to equal 0 when x is equal to 1. 3x plus 1 could equal 0 when 3x was equal to negative 1, and that would be x equaling negative 1/3. Then x squared minus 12 could equal 0, where x squared equals 12 and x equals plus or minus the square root of 12. And then, okay, there we go, 4 solutions, 4th degree equation. Okay? Not going to have 5 solutions to a 4th degree equation. I think that's the point I wanted to make. Okay, on B, let's look. 1x to the 4 minus 5x to the 3. Let's add the coefficients, see how it's going to go. 1 minus 5 is negative 4. Negative 4 plus 8 would be positive 4. 4 plus 16 is 20. 20 minus, and with a negative 20, okay, I'm seeing this is going to be 0. 1 will be a root. Always try 1 first if you're in my algebra class. Said it once, I've said it many times, always start with 1. And if that doesn't work, try negative 1. And if neither of those work, you might need to double check your work in my class. Not true just overall in algebra problems, but in my Algebra 2 class, start with 1, then try negative 1. If neither works, double check your work. All right, so 1x to the 4, negative 5x to the 3, positive 8x to the 2, negative 20x, and positive 16. I guess I should probably throw in the disclaimer, unless I'm giving you one of the roots or one of the solutions. If I give you a solution, then all bets are off, right? But you're not going to have to go make a huge list and try all of them and fail a bunch of times before you succeed. That's not going to be a good use of our time. Oh, right, so I factored out that x minus 1, and then I've got an x to the 3 minus 4x to the 2 plus 4x minus 16. I'm seeing parallelism. 1 to negative 4 is the same ratio as 4 to negative 16, so I know I'm going to be able to group and factor. Factor out an x squared plus 4. Oh, yeah, I remember. Yeah, that's why I liked this problem. This is like group and factor again, like not the first or the second time I've done group and factor in this video, so didn't really understand what the point was. Point here, wait, that was x minus 1. Okay. So x minus 1, x minus 4 times x squared plus 4. And all right, now I've got them all down to where I can solve them. Okay, x equals 1 here, x equals 4 there, x squared plus 4 equals 0, x squared equals negative 4. That's not good. Okay, that's not going to produce any real solutions. So we're just going to say x equals 1 and x equals 4 are all of the solutions to the equation that we can find today. You know, very soon we'll be able to find more, the other two. Okay, so now I think, hoping it's going to, speed up a little bit here, because I'm at almost 49 minutes into this video, and I've still got a couple pages left, so I'm just hoping this goes faster. Okay, we're going to use the degree and end behavior to match the polynomial to its graph. Okay, so this looks like degree 2 with a negative leading coefficient, okay, because one turning around spot and both the arrows are going down, so that there's evidence of a negative leading coefficient. Okay, this looks like degree 2 with a positive leading coefficient, because it's an upward facing parabola. Okay, this looks like degree 3 because there's 2 turning points. It goes up, down, up. Okay, so turned there, turned there. Okay, it looks like a positive leading coefficient because the polynomial is overall increasing. And this would be a, well, I don't know, but maybe an odd degree. And the leading coefficient looks negative because as I move to the right, the thing's going down. Okay. Is there something with, wait, a sixth power? Oh, okay. Well, I guess it's like could be. So degree 2, I guess this is like could be even degree. Okay, even degree with a negative leading coefficient. That's going to be this one, A. All right. Degree even with a positive leading coefficient. That'll be over here. Okay, and then that's got me concerned, but I see what they did. Okay, you just got to be careful. This is a 5th degree polynomial, so negative x to the 5, 3x to the 4 plus x. That's kind of a dirty trick. I try not to employ that trick very often, if at all, in my class, but every once in a while I'll just copy a problem from somebody else, and I really don't like the hiding the highest power term in the center of a polynomial. You know, like, I'd say, obviously, the traditional standard form that we're used to, where descending order of powers is fair game. Also fair game is where, like, 1 plus 2x plus 3x squared. That's definitely, there's nothing unfair about me giving you something like that. But putting the highest power term in the middle of the polynomial, I probably won't do that. Okay, so odd degree negative leading coefficient, that's this one. That's going to be answer choice D. Okay, and 15, that's, what have I not used? C. Okay, odd degree positive leading coefficient, yeah, great. Let's move on. Describe the end behavior of the polynomial functions. Oh, okay, that's a lot of room to do that, but this is a 4th degree polynomial. So what matters about that is that it's even. The leading coefficient is 3, and what matters about that is that it's positive. Okay, so the end behavior is going to look like this, but what I'll tell you is if I ask you a question that's like, hey, what's the end behavior? I expect you to give me something back, something a little more sophisticated than 2 arrows. Now, I might give you a multiple choice question that asks you to choose from sets of 2 arrows that describe the end behavior, just so that you don't get caught up in infinities or something. But if I ask you to produce the end behavior, I expect that to be written in a sentence, at least one sentence. So I'm going to say, as x approaches positive infinity, or negative infinity, the same thing's happening. Y is approaching positive infinity. Okay, that's one sentence that catches both of the arms of the end behavior, and that's it. Okay? But sentence, okay? Better than that. A little more sophistication. All right, this is exactly what I was talking about, except, you know, maybe I forgot an x cubed in here. I copied a lot of problems on this one. You know, increasing powers of x, it's completely fine. Right? This is a 5th degree polynomial. Which is an odd degree. The leading coefficient is -2, and what matters about that is that it's negative. So that means that overall, it kind of looks like the graph of y equals -x cubed, but I need to do a little bit better than drawing 2 arrows. So I'm going to say as x approaches positive infinity, y approaches negative infinity. That's this one right here. Maybe I'll circle that one in blue. Okay, and then as x goes back to negative infinity, y is approaching positive infinity. And I might emphasize that in red. Okay, now we're going to use the graph to describe the degree, leading coefficient, intervals on which the function's increasing or decreasing, and intervals on which the function's positive and negative. I like that. Okay, so I think the first thing is going to be to label our extrema. This is not quite right, but I'm just going to say this is happening at x equals -2 for the sake of argument. And it's going to be x equals 3. Okay? So degree is going to be odd because the 2 arms are going in different directions. Okay? Or, yeah, actually that's going to be why. Odd degree, most likely 3rd degree, because I'm seeing 3 roots. But can't say for sure. The leading coefficient is going to be negative because it's going down as I move to the right. Okay, as it turns out, that's a sufficient condition. You don't even need to worry about the left arrow, right? Is that if on the right we're going down, that means your leading coefficient is negative, regardless of if the degree is even or odd. I'll just let you think about why that's true. Okay, B. Oh, okay. B is supposed to be intervals of increase and decrease. Okay, okay. Increasing is between these 2 points, so from -2 to +3. Decreasing is going to be really everything else. X less than -2, also x greater than 3. Increasing, decreasing, positive, negative. Okay, so it said, yeah, first it said negative. Okay. F is negative. Maybe I'll underline kind of with squiggly red on where the graph is below the x-axis. That's what it means to be, for a function to be negative, is its y-coordinate is negative. Graph is below the x-axis. Okay, so negative is happening from -4 to 0. And also when x is bigger than 5. And then it's positive, well, really everywhere else except for where it's equal to 0. So I might put this in here. All right, so F is positive at a time when x is less than -4, over here. Also when x is between 0 and 5. And then we're going to lastly sketch a graph of a polynomial function f having the given characteristics. So, all right, I think what I'm going to do to make sure that I've got, you know, like the structure in place that I need to get all of these things is I'm going to look at all of the x values. Okay, so these are like x intervals, not coordinate pairs, right? To infinity is not a point, right? It's an interval. So I need x equals -2, x equals 0, x equals +2, x equals -3, -1, +1. I think I'm going to label -3 through +1 and just all of them. And just be bold. Okay, so -3, -2, -1. I guess you probably didn't need to watch me fill out my number line, but I suppose you could always fast forward through this. And who cares if they're evenly spaced or not? All right, and I think that this is the type of problem. I got a lot of, you know, different things going on here, specifications I've got to hit. I might use a pencil just in case I mess this up, right? I don't want to have to go through and erase this whole thing on using whiteout tape. Oh, I don't have much in the way of pencils in this drawer. It's not looking good. I do have this. This will have to do for now. All right, increasing from -2 to 0 and 2 to infinity, and then it's decreasing from -infinity to -2. Okay, so I know I've got to have a relative minimum at x equals -2. And f of x is greater than 0 from -infinity to -3. Okay, so I know that this is a place where it's changing signs. And from -1 to 1. Okay, so I have a feeling that -1 and 1 are both locations of sign changes. And then, what was I thinking about this one? All right, so I've got, okay, what's happening between -3 and -1? F of x is less than 0, so it's negative. Okay, so that means that this minimum is happening right there. Okay, that's good. I've got a little bit of graph going. Okay, and then I assume that f is going to be positive from -1 to 1, right? Yep, okay. And did it say where I had a maximum? Oh, no, okay, it did not, but it said that it's decreasing from 0 to 2. So I assume it's going to go from increasing to decreasing here. There's going to be a maximum. Decreasing 0 to 2. Okay, it looks like x equals positive 2 is going to also be a minimum. I assume from 1 to 3, the function's negative. Okay, I don't really understand what the point of the interval from 1 to 3 was that we didn't already get on this interval, but that's all good. We're going to go up there. What about from negative infinity to negative 3? That's where f is positive. Okay, it's going to look like that. That was a lot of effort. I'm probably not going to ask you a question like this. Okay. Oh, one thing I was going to point out is that if they asked you what like the minimum possible degree of this would be, I would say 4 because of 3 turnaround spots, 4 roots, even degree. Both the arms are going the same direction. That's all I got to say. I'm over an hour. I'm going to end this now. Thanks for watching. I really hope this helps.